So here's these three formulas that I think we've already showed, but I want to kind of overview them first and give some English translation to them. So the work done by the Coulomb force as a charged particle moves along the path A to B. So those, there's like a 2-minute silence there. Lose my radio job by the dead air. All right. So the work done by the Coulomb force as a charged particle moves along the path A to B up there in the pink. Just any work integral would have that description. The difference would be what force you're talking about, along what path L you're talking about. Potential energy can be defined as the field relative to its distance between points along the path. And then the potential difference is related. So these things are all layered, stacked on one another mathematically and conceptually as we move from one to the other. So just sort of a little bit of review from the prior stuff and put some English on the mathematics. All right. And here's the thing is if you can have an English version of a work integral, then that means you can understand any work integral, whatever the work is about. It wouldn't matter what the force is or the path. So we have those basic pieces of the puzzle there. All right, I'm going to move on and talk about the potential gradient. As I recall, some of you have had some exposure to div, grad, curl, and all that in your calculus experience. And so let's dig into it. So the way we're going to start with this is something that is familiar, and then we're going to expand why we need to go with partial derivatives. The gradient is a vector form of a path integral, and you have to deal with the directions. How this is changing in that direction, but the other directions aren't changing. So we have this difference in potential that we've seen before. It happens to be equal to the dot product of the field and the path length along the path. And so this also equals the integral, the negative of the change in potential difference, d capital V, all right, which you can also be written, by the way, if I reverse the order of the path, then it's a positive potential, right? But basically, we're able to write this integral of that differential on the potential field, the potential difference, and write it this way. So we have that baseline. Now from this, we can just drop the integrals and go straight to differentials. Remember, the dot product produces a scalar, so I can have a scalar differential equal the dot product of something else and a differential, all right? And we have this going for us. Now here's the thing, E. The vector E could be written this way. And I'm going to use IJK notation. I'm also going to do something similar to like we saw in Python. I'm going to put the vector pointer out in front just so it doesn't get confused with things. So the x component with its magnitude, the y component with its magnitude, the z component with its magnitude. You could also write this way. I prefer this bracketed form, but a lot of representations happen with that IJK. You're going to take a linear algebra course, and it's going to be IJK to death. If you're electrical engineer, it's going to be IJK to death. So since you're going to be IJK to death for a while, I might as well begin soften, get you ready for the game. But the way you're going to compute it is going to be in brackets like the last part. In MATLAB or whatever computational array you use, you're going to put it in rectangular form and do various vector manipulations in that latter form. But what it means is in the larger expanded form. So this is what E is. Okay, so we got to make sure that we attend to that without any things. But what about DL? Well, DL would be the same sort of thing, except it's going to be differential links or dx dy dz. So that's what DL is. These things that we're dotting together have vector parts, and that means the change has to be accounted for in all of the parts of the thing, but you can only account for one change at a time. All right, you can't account for all of the changes at the same time. You account for them one at a time. And so let's finish the deal here, though, at least initially. What this means is that my differential on the potential field, dV, would therefore equal the x component of the field and the path, the differential chunk of path length associated with it, EY dy plus EZ dz. All right? So what have we done? We've gone from a regular integral form for potential difference. We've reformulated that in terms of the way that the vector parts of that actually are. And now I have a vector magnitude version of this differential on the potential field. So magnitudes of field in those directions and infinitesimal chunks of path length in each direction. All right? So we get some mileage out of this, hopefully. So let's see here. Suppose that delta L is parallel to the x-axis, all right? Which means my dy and dz chunks are 0. And what this means is that my minus dv equals just the ex dx, and therefore the x part of this puzzle is a minus dv dx, where the y and the z parts are constant. So only x varies in this derivative. This is a partial derivative because the potential field has x, y, and z components, but with this particular supposition, we basically have a partial derivative. All right? So you learned about partial derivatives. In fact, I think they even show it to you initially in Calc 1 for about 38 seconds. Then I think Calc 3 is where you really get to use it. Is that right? 2 or 3? Both of them, you were using some partials. You used it a lot in 3, if I remember right, a little bit in 2. All right. So just sort of want to bring you back to those things you know about partial derivatives and why you would use them. You can use them. That's what you learn in calculus. Why you use them is this is one reason why. I have changes in multiple directions of an entire vector field, and so I absolutely have to do partials. And then we're going to come back and really put this on steroids when we do Maxwell's equations. All right, so the wave equation, all that jazz. All right, so what this leads to, the next part continuing, this means that the magnitude of my EX field, the X part of my field, is actually equal to the partial of the potential field relative to the X. Means EY has the same form, this partial of the potential field, dy, and EZ. So each component of the electric field can be understood in those terms, partial derivative terms, and so these would be components, oops, all caps here, of E in terms of V. which means I could write my electric field vector as follows. So I'll write it all out, and I think you'll which is the same as writing it this way. Which has been compactified and defined in terms of the del operator, which is called the gradient. Okay, it's basically the slope of a surface. Okay, so if you've driven to, say, Flagstaff or something, you'll see the sign, grade 5%, 6%, whatever it is. It's a gradient. But it's the slope of a surface instead of the slope of a line. And surfaces are defined in multiple dimensions, at least 2. Okay, real surfaces, 3 dimensions. All right, and so that's why they call it the gradient. All right, and so this vector calculus could be oversimplified as div, grad, curl, and all that. Grad is what we did here. The divergence is similar, and the curl, that'll show up later when we do Maxwell's equations. But it's about the way these fields interact and the kinds of surfaces or patterns they produce in space. Okay. Of course, a surface is an interpretation of a pattern in space. All right, whether that space is really shaped that way or not is another question. We'll leave to someone else to become a theoretical physicist and get their Nobel for determining whether or not that's real. All right, so we have this, and so I want to add some things here, but I need some space. I'm gonna try to move. Oh, that didn't work out so good. Guess I can't move things like that. So let's see here. I'm just gonna have to make a new screen. Right off here. So at each point, the potential gradient points in the direction towards increasing voltage. So I'll just use an arrow, an up arrow, voltage. Or let me relative to a change in position, L. All right? Another thing to section off. The direction of E is towards decreasing potential. This little factoids, and you should be able to read these in your book or anywhere that you would look up something about these things, but just those would be interpretations of these equations, but they are critical to what we do. So here, given that voltage, and we saw this the other day, can be written as Q for 4 pi epsilon naught R, or KQ per R. Find the vector E. So this is us letting us use some of this stuff we just worked on. So for a radial field, which is what you pretty much always have, but in a single point charge it's all extending out, all right? So we can write E sub r, meaning for the radial direction, and according to what we just worked out, that would be this partial of the field with respect to r, which would be the minus ddr of what we just saw, 1/4 pi epsilon naught q per r, which means E sub r, be careful here that this r is understood as a subscript, not a multiplier. Then what do I get? I get 1/4 pi epsilon naught q per r squared, which is exactly what you expect. Coulomb's law. So it's as much as possible, try to bring it back to the starting point. So the math gives us back what we expect. If it didn't give us back what we expect, then something's wrong with that math, or what we put into it, or both. All right, so these sorts of checks are essential to the game called science, engineering, etc. And so if we were to make a vector out of it, we would have those things so this, you could understand this is, if you wanted to have magnitude and direction, that would be a way to understand what we did. So what if we ignore the radial symmetry and write the radial distance as good old Pythagorean radial distance. Okay? Well, that'll be fun for the whole family. So, basically,
this means that our for the x part of the field, we'll get it one part at a time here. We're going to have the partial with respect to x of 1 over 4 pi epsilon naught, the k constant in Coulomb, and instead of q per r squared, we're going to have, or q per r rather, we're going to have this other version of r. Well, the partial, so we'll have a don't forget our negative. And so when we do the partial with respect to x, y and z don't change. And so q is a constant, so we'll get an x out of that, but then we'll get all of that in the bottom to the 3/2. Little derivative fun for everybody there. All right. Well, really, isn't that just r cubed? Isn't that to the 3/2 just r, which was that thing to the 1/2 cubed? That really is just r cubed. And so we just get a minus qx for 4 pi epsilon naught r cubed. Well, that means the y version is going to work out exactly the same, except you have y in the top. Which means your z version will work out exactly the same, except it'll have z in the top. Interesting. So the potential field has an inverse cube structure to it. Well, in terms of the math, you'll still have meters squared since it's a length over length cubed. Okay, but the separation distance, z isn't the separation distance, r is. So we have an inverse cube-ish sort of thing. All right, so ignoring the radial symmetry and going Pythagorean on it leads us to some interesting pieces of partial derivative of the potential field in XYZ directions, which all have the same basic structure minus the XYZ part. All right, so what do we do with that? Well, good question. Glad you asked. That means that if I write my E vector, so we'll kind of repeat the drill that we did earlier, except the innards are a little bit different. So the IJK structure, again, so I can pull out all of them Q's, the 4 pi epsilon naught r cubed. Well, actually, I'm going to pull out an r squared, and I'm going to leave behind, notice the minuses canceled one another. I'm going to leave an r in there. Yay, we get back the Coulomb version from all of that. All right, so just in case, that's coming from there. That's coming from there. And that it's there. Just a little vector calculus to ruin your day with. All right? So there is a little bit of heavy lifting, semi-heavy lifting involved in the doing of all this stuff. This is here because it's legitimate here. Plus we, like I said, we keep ramping up towards Maxwell's equation. The wave equation is more of the same, partial derivatives, and that's how Maxwell did his thing with that. So, quick little example to kind of lay that. So one last thing. And by the way, this sort of thing, I mean, this is what scientists do all the time. They make sure that the particular application corresponds to known laws. And if I can't get back the fundamentals, something's wrong. And so you go figure that out. All right. So let's have a conceptual exercise here. So let me draw something here. So I'm going to have 2, 3. So we're going to go from 30 volts, 5 volts at a time to a 5 volt line. So this is a potential field, all right? And and 6 steps in that potential field. And then if I have another potential field, 6 steps with the same changes, but they're compressed a bit. And then another one. Where they're stretched out in a more unusual way. And so the question is, and we need to, I got to put a point P in, but I'm going to type it in here. Rank, order, the strength of E at P. So where is P? All right. So let me get a good color here. And P is going to be on the 25 volt line each time for situations 1 through 3. So the trick here is rank order the strength of the electric field. Now there's a number of ways that you could understand the strength of the electric field. If you make a gravitational potential, like a topographical map of, say, a mountain, a surface on Earth, the more concentrated the lines on that map, the steeper the hill. The farther apart the field lines, the flatter it is, okay? And so I think we could immediately know that situation 2 is the steepest
All right, in a gravitational analogy, 2's the steepest, 1's the next steepest, and 3 is not that steep at all. So just the gravitational analogy tells me that field 2 would have to be really big. Field 1 would be half as big, and field 3 should be 1/5 as big, or 1/6 as big. All right, so it should be the case that E2 is greater than E1, which is greater than E3, just by the gravitational analogy. That's one way to go about it. Another way to go about it, and I've said it a couple times, I think, and it's the same thing as what I just said, but any field map, the more concentrated the number of field lines, the stronger that field. So a single charge would have, say, if a single charge had X field lines, twice that charge would have 2X field lines. More field lines, bigger field, every time. The concentration of those field lines, more intense in that region where they're concentrated, less intense where they're spread out. All right? Those are easy ways to go at it. You could, however, have a different view, given that the Coulomb force if I do work per unit charge, I get K Q per D. So let me it's not letting me erase my there we go. Give myself some room there. And of course, KQ per D is going to be the potential per Q, which is voltage, which is the same as electric field times distance. And electric field is volts per distance, or if you remember back to the FET diagram, or the simulation, which you've used 3 or 4 times now, what was the electric field? It was volts per meter, which is the same as newtons per coulomb. Okay? And so the number of volts per distance. And so I have a shorter trip. So every, in situation 2, it only takes half the distance to go 5 volts as it does in situation 1. And in situation 3, it takes 6 times the distance, or 3 times what it is in situation 1 to go 5 volts. So you have a less intense field by those measures. And so there's a gravitational analogy, there's just the rule of thumb about the number of field lines in a region of space, and then there's the math. Quite literally the slope. I managed, this is basically a flat, 2-dimensional flat surface gradient. All right? The equivalent of a line graph. V per D, that's slope. That's regular old slope. And 1-dimensional slope is a gradient, just the easiest gradient you can imagine, because you only have one part changing relative to a one-part thing. All right? Whereas the gradient field in calculus involves 2 and 3 multiple dimensions and all that. So that's just a way to understand. Equal potential surfaces takes some time to get your mind around it. And you need to look at the pictures, you need to look at the math, multiple versions of the math, and really soak in that for a while. It takes some time. So anyways,